Hello everyone. Today I would like to talk about an enhanced metrological protocol for the determination of biofuels calorific value. So the scope of this presentation will be the following. So I will talk about the metrological challenges associated to the determination of the energy content of biofuels, and the scope of work package 1, and in particular task 1.2, the experimental setup that has been used, and the results that we obtained, and analyzing these results, and the uncertainty budget of these measurements, and eventually the future work. So the calorific value has several challenges. So basically, there is a lack of a technical protocol that addresses the difficulties during the sample measurement, in particular something like the sample heterogeneity. So there is no clear information that tells you how to handle samples that is very homogeneous. So there are gaps in the calorific value standards. There is a lack of defined uncertainty budget. So if you wanted to measure the calorific value according to standard, you would be able to do that, but you will not be able to determine the uncertainty. There is no protocol or a defined protocol to do that. So these are some of the challenges that we will try to address in our task. So, but the question is, why is it important? So that would be a very interesting question because it has different aspects. So first, from a financial point of view, so the financial perspective. So when you would like to purchase a biomass, you will purchase it basically based on its properties, its energy content. So if this value is not right, that means someone is losing or gaining money. So whether the end user or the provider. So from a financial point of view, it is very important. From another scope, also from an operational and process design perspective. So when you would like to design something like gasifier, for example, you would like to have a clear information about the physical properties of the samples that you supply to the gasifier. So it is a crucial element when you would like to design a process. You have to know how good your feedstock is. So that's why it is very important that we well define and characterize that biomass. So in task 1.2, what we did basically is we developed an improved traceable methodology to address the challenges associated with the calorific value. We provided a detailed uncertainty budget to harmonize the measurement. And by doing that, we actually assured there is a fair biomass pricing. So here to zoom out a little bit, so in order to decide which kind of samples we would perform our investigation upon, so we made a survey within the scope of our task to try to know which kind of biomass that's widely used in the industry and the end users are consuming in order to test on those samples. So the final result was as following: 25% wood chips, 25% like wood billet, and 25% biodiesel and some other substances. So based on that, we decided that we will have to test wood pellet, wood chips, and biodiesel, which are the most common types of biofuels that are utilized currently in the market. So in order to measure the calorific value, the experimental setup was basically as following. So we used a pump calorimeter. So this is basically, as you can see in the left side here of the screen, it's basically about having a charged sample in a crucible put under oxygen pressure, high oxygen pressure of around 30 bars, and this is a charge and connected to electrodes. This pump here will be placed inside a bucket of water which has stirrer. When the sample burns, a heat transfer will take place from the sample into that metal and from the metal to the water, causing the temperature of the water to increase, and by that we can calculate basically delta T. So basically that's what you also can see on the right side. This is an instrument that we're using from BAR. So here, this is the water pocket. You can see the pump itself placed inside, and here the connections of the electrode. So that's basically the first equipment that we use. After combustion, after complete combustion, we release that oxygen and we collect the liquid that will be gathered inside the pump. So what we do with this, basically, we determine the content of this liquid, which basically contains anions, mainly the NO3 and SO4. Those are the ones that we are targeting because they are contributing in the calorific value, and we have to do that correction to obtain the correct calorific value. That's why it's very important to determine those elements. They could be determined by ion chromatography or titration. In our case here, we show the ion chromatography. So basically, we're using ion exchange chromatography with chemical suppression. So as I said earlier, you determine several anions. Then the main ones of interest are NO3 and SO4. And basically, they are being separated inside the column, inside the instrument, based on the affinity to attach to the column. So after we calculate the NO3 and SO4, now we can actually have the calorific value. So now we had a methodology to determine, to try to improve the measurements. So basically what we did is perform two different test cycles. Cycle one was basically based on the ISO standard, so we did not try to do any changes. So we stuck exactly with the same way how the standard is saying what to do. So you can see here that the results are widely scattered, whether if you consider the wet basis or the dry basis. So you can see that there is a significant difference between the data. So from 1,800 around 19,000, 1,000 joules. While if you look to our improved practice, you can see here that the data are more concentrated about around the average, whether on a wet basis or on a dry basis. So this was the first sample, which was basically wood chips high quality. Then we tested another wood chip sample. So again, you can see the samples here relatively scattered. Here is relatively better, but still the samples after our improved practice is significantly better. Then again, on wood billet, relatively a similar behavior, not the best compared to wood chips here, but you can still see that they are concentrated around a very small range. By that, the data looks much better. So now, in order to understand what we changed and what was the reasons of this improvement, we try to do a root cause analysis. We wanted to understand why the samples are deviating in the first place. So we have a scattering, and there are different possibilities. So basically, you have a poor sample lot representativity. For example, we took a patch that's not really representative. So the lot itself is not representative, that there is potentially a moisture loss that happened. So, or the patch heterogeneity, the patch itself is just, this is its characteristics, or some deviations in the experimental practice, different practices. Even so, we use the same standard, but since the standard does not cover everything, so the user might do something and another user do something in a different way. Maybe that's one of the reasons. So that's what we try to analyze. But to go more in depth, so you'll find that the poor sample representativity comes from two possibilities. Sample portion is maybe small, or there was just a poor mixing. So while the moisture loss could come from different grinding instruments, of the people use different instruments, and the batch heterogeneity would be connected directly to the properties of the sample itself, so the different composition or the different impurities content or the different moisture content. So then again, when you expand the different grinding instrument, why they will lead to different moisture loss? Because heat generation causes drying. Then the different composition, why it will influence and cause scattering? Because basically the concentration of the cellulose, hemicellulose, and lignin portion could potentially be slightly different, or in the impurities, the organic and inorganic might be different, and you have the moisture content, so the determination errors could be because of determination errors or the equilibrium moisture content. And this one, the equilibrium moisture content, EMC, will be one of the important factors that we will discuss here as well. So in order to know what was the reasons behind this deviation, with all these parameters, we can't specify a specific reason. For that, we wanted to remove some of these elements to determine the possible cause. So PTB provided a well-mixed, grinded, and unified samples. So those samples will help us eliminate some of those factors. For example, the moisture loss that differed because of the different grinding instruments. Now, this factor does not exist. Such factors will, the per sample representativity will also change because we have a one institute provided the samples. So when we use Topitak samples, which was in cycle 2, we found the following. That leaves the reason of deviation is concentrated in those parameters, in the batch heterogeneity or in the different experimental practice. And that's what we will stress on